In this demonstration, you'll learn how to perform a basic fluid flow simulation using a template. To begin, from the list of simulation process templates, I'll pick Fluid Flow, and there I can find some options to customize the template. I know for the geometry I'm using, the flow volume will need to be extracted, so I'll import an existing geometry and select Full Model Editing Capabilities for the Geometry option so that I can create the flow volume. I'll click Create Simulation Process and select my geometry. AIM will use that geometry and the template to build an outline of a fluid flow simulation. The geometry is now visible. It is a manifold with 3 inlets and 1 outlet. I can also see that the template has produced a number of tasks, many of them incomplete that I, as a user, have to complete. This is the advantage of using a template. The framework of a basic fluid simulation is automatically created for me. I can still customize the simulation process to meet my needs as I go. To start, I see the geometry task is complete, but I still need to edit my geometry so that I can extract the flow volume of the manifold. I'll click the Edit Geometry button, and now I can access the options to perform the volume extraction. I'll go into the Prepare tab and select Volume Extract. I'll select the faces that enclose the region. I'll also select the seed face, which will determine the inside volume of the region. Make sure to click the check mark to create the flow volume. Selecting Edit Geometry on the top left of the graphics window will save my extraction and take me back to my physics simulation. To better see my extracted volume, I'll hide the structural body using the Body Selection tool and right-clicking Hide Body. And I'll similarly select the Hide Edges tool to hide the edges. Moving along the workflow view, the next task I need to complete is the meshing task. It has an attention required message, which means I need to do something to complete the meshing task. The flow template has created an inflation control, as most fluid flow cases would require inflation to model boundary layer effects. I need to pick a location for the inflation layers, and this needs to be the inner wall of the manifold, which corresponds to the outer wall of the flow volume. The rest of the defaults are fine, so now I just have to right-click Generate Mesh to update the meshing task. I'll zoom in to inspect the inflation layer by dragging my right mouse button and holding the Shift key down. In the physics task, there are a lot of options, but by using a template, many of them have been set for me. For instance, since we are using a flow template, a fluid flow physics region has been created. This defines what type of simulation will be performed and where the corresponding equations will be solved. Currently, I am only solving for the flow field in the manifold. If I was interested in the temperature field, I could also activate thermal here, but for this demonstration, I will stick with just fluid flow. For the location, I want to make sure the manifold is treated as a single flow volume, so I'll select the entire body to represent the flow region. Notice this conditionally up-to-date message. If I click to learn more about this message, it'll take me to the Messages tab, where I can get more guidance on what I need to do to make sure my simulation is fully up-to-date. Going back to the physics task, I want to check what material the template has assigned for me. It has used air, but for this simulation, I want to use water, so I'll select it from the drop-down. I can see the properties for water by expanding this panel. Back to the physics task again, I see by the blue button that I need boundary conditions. I'll close this panel because I can set up most of my physics by the right click of a button. I'll select this face and right-click. Following the blue arrows, I'll go Add, Boundary Conditions, and choose Inlet. Now a small property panel appears and I can enter some information about the inlet boundary condition. I'll enter a velocity magnitude of 5 meters per second and press Enter. The icon on the model tells me that an inlet boundary condition has been added on this face. I can edit the boundary conditions by just clicking on this icon and the property panel will reappear. I'll repeat this process for the other inlets using velocities of 7 and 10 meters per second, respectively. I'll select the opposite end of the manifold and assign it an outlet with a gauge static pressure of 0 pascals. Finally, I'll create a wall boundary. By default, this will be assigned to all the faces which have not previously been defined by boundary conditions. Now all faces are assigned a boundary condition, and I can proceed. I can see that the physics task is no longer in a state of attention required, but now out of date. This means I have fully defined the task and can now solve the physics. I can monitor the solution by opening the Solution Monitors tab and watching the residuals update after each iteration. The solution is now complete, and we can move on to viewing the results. The fluid flow template has created a result for me. It's a velocity vector plot. All I have to do is update the results task to see it. And here it is. It looks a little sparse, so I'll increase the number of symbols from 100 to 500 and reevaluate. This concludes this demonstration of using a fluid flow template in AIM.